Okay, we're slightly late. I'm sorry. You can have a break and have lunch. I'm not going to be offended if you're chewing while I'm talking. All right, I'm an astronomer. So as an astronomer, I always bring my telescope with me. All right? I will explain why I have this later. Okay, so my name is Franck Marchis. I'm a researcher at the SETI Institute. I'm also an entrepreneur. I'm a co-founder of a company called Unistellar. We do telescopes for everybody. Today, I'm going to talk to you a bit about what SETI is about, the SETI Institute, some of the work we have done using Web3 technology, and then I'm going to discuss a bit about Unistellar and where we want to go and how we need your help, because I'm discovering this world, as I mentioned already, and I really need help to be able to do this project. So this is the goal of my presence here, is to learn from you and hopefully to get connection if you're interested in working in this new project. Okay, so the question we ask when we look at the star is whether or not we're alone. And that's the question, the motivation, and the reason for which SETI Institute was creating 40 years ago, 40. When SETI Institute was created, I don't know if you know the story, it was basically because NSF and NASA pulled out the funding, and some researcher decided that this is a questions way too important for us to give up. So Frank Drake, Jill Tarter, Tom Pearson, those people decided that they're going to create an institute and get private funding to do this research. We basically, it's in our DNA at the SETI Institute to be always the bad boy, the one that doesn't say no as an answer. And the Institute has been like this for 40 years. Just to give the context, when we started the Institute, I did not start the Institute. I joined the Institute 15 years ago only. But when I joined the Institute 15 years ago, we had no idea that our galaxy was made of 400 billion stars, and that around each of these stars, in average, there is 2 planets. We call them exoplanets. And we didn't know that most of those exoplanets are Earth-like exoplanets. So now we have a number, a very interesting number. We know that there is at least 300 million planets like Earth, potentially habitable in our galaxy. And this is just our galaxy. We have 3 trillion galaxies in our universe. So when people ask, are we alone? I will say it's very unlikely. It's very unlikely because of the number of potentially habitable worlds we have in our galaxy. And this is something new. This is something that we discovered in 2013 after the launch of the Kepler mission. And this is a paper that mentioned, the number I mentioned, a paper that was published 3 years ago. Now SETI became mainstream because we know that there is potentially life elsewhere in our galaxy. So there is 100 researchers working on this question at the Institute. We have a friendly race between each other. In fact, there is 3 ways to find the answer to this question. The one that you probably know is the search for technological signatures by listening to the cosmos to see the presence of these technological aliens, for instance, listening to radio or looking for lasers. Another way is to look in our close neighborhood, in our solar system. Is there life on Mars and Enceladus? How this life form? This is what we call the field of exobiology. We diversified SETI Institute 15 years ago, and now we have half of our researchers working on these questions of finding life in our solar system. And then more recently, because we know they exist, we are looking for life on exoplanets, planets in orbit around other stars. We're developing technology to be able to image and one day get a picture of another pale blue dot, a picture of a planet like Earth, an Earth 2.0, not far away from us. So that's the goal of the Institute, and that's why we wake up at the Institute every morning, to find this to answer to this question by using one of these ways. But SETI Institute is not only that. It's also an institute located in the heart of the Silicon Valley. As I mentioned, we have survived without federal funding for quite a long time, thanks to donations and to partnership with private industry, with donors, people who basically created computers, joined us in the 90s, and then we diversified. I do remember the first time I heard about AI at the Institute was 12 years ago when we put together a program so NASA could basically investigate how AI could be used to answer to questions about space. So we've always been at the avant-garde, at the front of technology, using new technology to answer to scientific questions. So we want to continue this, and that's why I'm here. And the one thing also is that you probably notice that astronomers are always kind of the bad boy of science. We always, and bad girls as well, by the way, we always been the one questioning the system. He started with Galileo Galilei, Giordano Bruno. This is a picture of him trying to understand how the star works and basically challenging the way the world, the way the politics at the time and the religion at the time was seeing the world. It didn't work well for him, but a lot of them managed to change the system. More recently, were Carl Sagan, one of the members of the SETI Institute in the 90s. And also we can talk about Franck Marchis. Those astronomers changed the world and changed the perception of the universe in the media using their presence and using their writing. So we continue to do this at the SETI Institute, I would say. You probably know some of the members of the Institute like Jill Tarter and Nathalie Cabral, who are often challenging the system and talking about the reason for which we do this research. So can we remove the bar on the top of this? Because then all my titles are gone. So in 1997, there was a movie that you probably have seen called Contact. And this movie was a movie basically describing what would be the consequences of a contact with aliens. Something interesting is that the aliens at the time were sending us prime numbers. Very simple mathematics. We learn a lot about the fact that communicating with intelligent species is not going to be easy. We know that because we have intelligent species on our own planet. We can, like the whale, chimpanzee, dogs, and so on. They are intelligent. They have their own shape and form of intelligence. And we have a hard time communicating with them. So we know that when we're going to find aliens, it's going to be very difficult to communicate with them. And this movie, released in 2016, called Arrival, basically describes that very well. We have, in this case, aliens, which have a completely different perception of the time. They have a nonlinear time perception, which makes it very complicated for us to communicate with them. So this is a question that we have at the Institute, and we do some research on this topic as well. And then we have done also a project. This thing does stop working, I'm sorry. Sorry. Thank you. By the way, we should thank him for doing all of this by himself because it's not easy. So thank you. So last year, we started a project with Daniela De Polis. She's an Italian artist called A Sign in Space. Have you heard about this? Who have heard about the Sign in Space? Nobody. Good. So I'm going to explain. So the Sign in Space is a project to simulate the arrival of a signal on Earth coming from extraterrestrial civilization. Daniela and two other people basically compose a message. And they send this message to ESA, the European Space Agency, who use the spacecraft called TGO in orbit around Mars to send to us this message in some kind of encrypted form that reached us on May 24, 2023. We did a SETI Live. I was the moderator of this, where basically we explained to the people what was happening, and when the signal arrived, 3 antennas in the world received this and basically collected this information and saved it for the people. So one question we had is that how are we going to save this message so we're 100% sure that nobody can alter it, and it can be shared quickly, and can be available to everybody. So that's when I approached Falcon, thinking about that their platform could be a solution to this problem. So this message was stored on Falcon has been then decoded and become, we're talking about 60 gigabytes of data here, and it's then decoded, meaning that the meaning has is not yet understood, but there is a main content of the signal, which is only 18 kilobytes, and is still on Falcon. We have more than 2 million downloads of this message on Falcon, and the project has, based on Daniela's statistic on the website, has touched 145 million people, considering the number of press and access to the websites we have, coming from 175 countries. So if you like mystery and you want to contribute, we still don't know the meaning of this signal. It's still available. So if you want to spend some time with your friend trying to understand that, join our discourse, and there is still people trying to crack the code, basically. So we don't know what these aliens, which are human in this case, are telling us yet. Another program that we started at the SETI Institute is called Laser SETI. So the project here is very simple. We assume that extraterrestrial civilization will evolve like us, and they will go from radio to lasers to communicate. So if that's the case, if we look at the sky, from time to time, if the lasers is pointing directly toward us, we may be able to detect them. Or if they know we are here, because they've seen our planet, and they have seen some activity from far away remotely, they will basically, they may want to communicate with us, building those gigantic, powerful lasers and sending us a signal. So Laser SETI is a set of instruments. I'm not going to enter into the details, but those are stations with 2 cameras that look at the sky continuously, and they will be able to detect one of these laser signals, even if it's extremely fast, like a few microseconds, it will be detected by the signal. We have 4 stations installed, 2 in Canary Island, 2 in California. We're installing a new station in Arizona, and soon we're going to have 10 of them all around the world, capable of observing almost 70% of the sky. These stations generate a large amount of data, 250 terabytes of data, things per 4 years, typically. So we are now storing them on Picnic, one of the Falcon storage provider, and they are available to everybody. So the point here is that we are using the Wave3 technology. We are learning slowly to use that, and there is still some work to do. But something interesting to me when I was putting together this slide is that it's possible that right now on the Falcon network, there is the proof of existence of an extraterrestrial civilization. Just a question of finding it, analyzing the data. And we hope that people will get motivated to write and build their own software to do this kind of analysis as well. Okay, so the new project we started in 2017 is called Unistellar. Unistellar ambition is to create a telescope which is easy to use, a telescope for everybody, a telescope that can be a cool consumer product if you want to observe stars, galaxies, nebulae from your house, that work in cities, and as well a telescope for education, so teacher, professor can use it in their school, and finally a telescope which is useful for science, where we can do investigation. So 2019, we released the first model called the EV scope, Equinox, and so on. And in January, we have released the new one, which is slightly smaller, called the Odyssey. And this is an Odyssey telescope. It works. Later on this afternoon, when we have a break, I may show you the sun with it if you want. You just need to go on the sidewalk, and it will be easy to do it. Because this telescope, it's very easy to use. It's a smart robotic telescope. It finds itself where it's pointing. It finds the stars, the sun, the moon, adjusts itself the image, so you can do observation and enjoy observing the dark sky from your house in less than 5 minutes. That's the goal. Those are some pictures that we can take with this telescope. Those are real pictures, okay, taken recently by some of our users. So you can see the Whirlpool Galaxy on the left. This is the Comet Atlas in the middle. And this is the Eagle Nebula, where you can see the pillar of creation, if you know your astronomy, which are here, basically. So those Those are cool picture, pretty picture. People are happy to do that. But we created Unistellar not only for that, we created Unistellar for science as well. So the network is growing. It's not anecdotal anymore. We have more than 10,000 telescopes all around the world. Those are people who bought these telescopes. You can buy them in Best Buy, for instance, here in the US, and we have distributors all around the world. So as I mentioned, you control them in an app. They do everything by themselves. You truly enjoy the observation. And then when you reach the point where you kind of master the telescope, you can also decide to participate to science campaign. So us, at the SETI Institute, we can send alerts to the network. So imagine a new supernova appear in the sky, an explosion of a star. You get a notification telling you, hey, there is this new supernova. Do you want to observe it? You take your telescope, you observe it, you collect the data, you send the data to our server, we process them, and we publish the observation. I'm going to show you a few examples. I'm not going to show you all of the science we do. I'm going to show you a few of them because we don't have that much time. Oh, and we don't do that by ourselves alone, of course. We have partners. NASA is part of this, and various institutions all around the world, in Charles University in Prague, Observatoire de Paris in France, and so on. And we're growing basically the network and the interest of multiple institutions around the world. This is, I think, the biggest, I'm pretty certain, is the biggest network of telescopes in the world. So we can truly see the sky anytime, anywhere, at any moment. I always say there is always a starry night in the Unistellar network. There will be always someone observing if I send a notification to take an observation. So this is a team that I mentioned working in San Francisco in our office. Those are researchers, astronomers, entrepreneurs as well, and they work with me on developing the citizen science for different type of astronomical topics like comets, asteroids, planetary defense, etc., etc. And these are some of the citizen astronomers. Remember, there is 13,000 of them, and there is more than 2,000 of them who already took some scientific observations. So we have a large community now of motivated observers. And the goal is that really to diversify astronomy. I don't know if you have been to an amateur astronomer club, but there is not that much diversity. But we are bringing this diversity with this new technology. We are having young people embracing and doing astronomy. So this is some of the example of the result. This one is a supernova. So a supernova is basically an explosion of a star that happen at any time. So this is the closest supernova that detected from the decade. It was in the galaxy, in the Whirlpool galaxy. It happened in May. So you can see the explosion is that line, basically. This is brightness versus time. And you can see the explosion of the supernovae. And you can see it in this movie as well, appearing here. So we have like 123 people who observed the supernovae 3 months, over 3 months. And this is one of the papers we publish in open access, reporting the discovery of the supernovae and its importance for astronomy. So that's one of the results of last year. We do more. We do stuff, more valuable stuff, more like local stuff, like planetary defense, which is the idea of defending the planet against asteroid impact. We know that there is more than 10,000 asteroids that could potentially impact our planet at any time. One of them crashed or burned above the atmosphere, above Berlin a month ago. And we basically observed this one as well. And we basically help refining the orbit of this asteroid. So we are doing this kind of research to protect our planet against asteroid impact, but also we participate to program with NASA. This is what it looks like when you look at an asteroid. It's not super impressive. It's a tiny dot moving with respect to the stars, okay? But what is important here is that the asteroid is also has a brightness change. And by looking at the brightness change, we can derive the shape and the size of the asteroid as well. And those are extremely important parameters to learn how to mitigate an asteroid if one will impact Earth. Talking about that, you probably remember that in September 2022, NASA sent a spacecraft against to slam into the moon of an asteroid called Dimorphos. And those are the observations we got almost live from NASA. We sent an alert to all our users around the world, especially the one living in the southern part of Africa. And we got multiple people observing this event. Like, for instance, we have here Susan Murabana in Kenya organized a star party, and people witness the impact of the DART mission against the moon Dimorphos. So what did they see? Well, they saw this. Well, it's gonna work. This is the asteroid. So this is taken with our small telescope, okay? So that's basically the impact of the DART mission on the moon, and you can see the poof, we call that, around shortly after the impact. So this was impressive. I was doing that live as well, and I was kind of speechless, frankly, that we could see that so well with our tiny telescope, which cost only $4,000 at the time. So this is this result was quite remarkable because we have multiple people observing around the world. 31 citizen astronomers did 4 of them observe it live, and we published this result in Nature this year. And in fact, one of our motto is that everybody who participates to this this campaign is co-author of the paper. So we have 31 citizen astronomers who have never done astronomy, for some of them, who basically became co-author of a scientific paper in Nature. Publishing in Nature was one of the goals. I've done it, so now I'm ready to publish in any other journal, okay? You know how scientists work, right? We did Nature, good. Now we can publish in other journals, make the data more accessible and easy for everybody. So that's one of the reasons I'm here as well. Okay, so this is the change we're having right now. We went from astronomy being kind of a small science for the elite, for the astrologers, to at the second revolution, a field with 400 astronomers that was developing instruments to land on Mars, for instance, to now to the year 2000, when we discover exoplanets. So that was a big revolution. Now in 2022, the ambition is to basically have what we call an astronomy for everybody, okay? Like an astronomy where everybody can participate to our research. And this is the goal of the Unistellar SETI network. So we have been working on other problems not related to distant objects. And one of the problems we have been working on is satellite constellations. So you probably have heard about the fact that we're launching more and more satellites, specifically to provide internet around the world. Starlink is one of them, but there is way more constellation. OneWeb started also. Kuiper is on its way. And we know that countries like Asia, like China, India, and also Russia wants to have their own constellation. So today we have approximately 5,000 satellites in orbit around our planet at low Earth orbit. And you can see the dramatic increase over the past 5 years, right? And in fact, predictions show that in 2036, there will be 80,000 of them. There will be 80,000 satellites in orbit at low Earth orbit around Earth. That's a tremendous change, and that's a problem. Problem because the more satellites you have, the more risk of collision you have. Collision implies the more debris, of course. Those satellites also have an impact on astronomy. They basically blur the image, or you will see bring some strike on the image. They also have an impact on radio as well for astronomers, which is important. And finally, we have the problem of regulations. Those satellites are being launched regularly and so quickly that, in fact, government agencies cannot catch up. regulation have not been in place yet. It's still a wildfire, is the wildfire west over there at low Earth orbit, basically. The first which arrive will keep the orbit. That's the idea. So we have been working on this problem, and we think we have we could contribute significantly to this problem. So one of the ideas is to map regularly using these telescopes, but also other telescopes around the world, the sky to see those satellites passing by. So this is what they look like with our telescope, for instance. You will see a streak for a few seconds, for 1 second. That's an asteroid, that's a satellite passing in the field of view. So with this data, we can collect, if we collect them, we can identify the satellite using non-database, derive the brightness, the location, etc. And the final result will be to be able to have an update of the orbit, to be able to know when there will be a close encounter between satellites, to warn, for instance, the manufacturer of the satellites, also to offer safe orbits. So if there is a problem, if there is a close encounter, you can warn a manufacturer of satellites, and they can modify the orbits so to avoid, for instance, a collision, or to make sure that the satellite is not being degraded by the passage of another one. So this looks anecdotal right now, but we believe that there is a serious problem, and astronomers could help fixing this issue with all these telescopes that we have now on the ground. So how are we going to do that? Well, I mentioned this multiple times to some of my colleagues, and one of my colleagues at Falcon mentioned the fact that we need to maybe organize this better than what we had in mind, create a marketplace, basically, for the universe. So the marketplace for the universe will be a place where professional, amateur astronomers, archive data, and other instruments will be basically sending their observations. And this observation will be stored such as they cannot be modified. Because there is a lot of political problems here. I mean, when you observe a satellite, you can observe a Starlink, but you can also observe a satellite that people don't want you to see for multiple reasons. So here, with Web3 architecture, we'll be able to make sure that data collected by those telescopes are being validated and can be traceable and cannot be modified by anybody. The end customer for that is all the new space industry. Everybody sending space satellites or even sending hotels in the future in space will want to know where are those satellites and if they're passing nearby them. There is also research institute and universities who have been doing a lot of research to understand the effect of the satellite on astronomical images. So for instance, one of my colleagues work at the new telescope called LSST, the Vera Rubin telescope, which is an 8-meter class telescope in Chile, which is capable of mapping the entire universe, the entire sky every 3 days. He has a gigantic, extremely sensitive camera. The last thing you want is this telescope to get affected by the super bright satellite passing in the field of view, of course. So this is something we could work with our data repository, building basically a tool so astronomers know, for instance, in advance when satellite will pass nearby an object of interest that they're observing. And of course, the governmental organization will want to have a clear idea of how many satellites are in the sky, where are they, who is doing what, to basically help mitigating potential collision. One issue we could have here is that if we have a collision, I didn't say that, I didn't emphasize that, let me repeat this, it will basically destroy partially a satellite, produce fragments. And those fragments, even small ones, have a speed so high that if they impact on the satellite, they will destroy this one as well. So we're gonna have what we call a Kessler effect here. Basically, we could lose complete access to a part of an orbit around Earth. Losing an access to the part of orbit around Earth means like losing access to communication in space mean as well not being able to send spacecraft in space or human in space. So that's why it's important. I mean, this is not something, we will not be able to live without access to, in our modern world, without those satellites in orbit around Earth. They are extremely valuable for multiple reasons. They provide internet, but they also help monitoring the environment, the weather, etc. You use them every day. So imagine suddenly we don't have that simply because nobody have done this mapping and characterization of the satellites around Earth. So that's the reason I think this is an important problem. And the way we could tackle this is with your help. So I hope some of you will be interested in discussing this later on with me and maybe brainstorm some of the way we could do that quickly. Because this is not something we can delay for the next, in 3 years. The launch of the satellite, the Starlinks, and the OneWeb, it's happening now. It's not gonna be able, we're not gonna be able to delay this more. Okay, I'm gonna conclude here. You have seen my talk. I'm not gonna read these slides. I just wanted to say thank you for letting me speak about these crazy ideas. I hope they're not too crazy for you, and I'm exactly on time, 30 minutes. Thank you. Any questions? Yeah.
So besides Bitcoin, the DeFi movement started with SETI with an incentivization layer on top on the virtual infrastructure for computing, holding at home, and those are the two mainstream computing technologies. So we can scale that very quickly. And we need to. So what do you need to scale that very quickly?
Oh, what do I need? I need people who understand this technology better than me. They can explain it to me and find a good way to create an incentive for people to do the observation and a good reward way. So, and this is something I'm kind of started thinking about typically 2 months ago. I need coders. I need some people who really gonna do the work because the 50 years old here is not capable of doing this by himself. No, we have 13,000 of them or 10,000 of them. So yeah, we can have more, of course. Okay, let's talk. Yeah.
One question. On these aggregate 13,000 telescopes, what's the data glucose that's generated in one day?
They gave me the number like 2 days ago and I kind of forgot. In 4 years, I think we something like 20 terabytes or something like this.
So this is manageable.
Is it manageable? Yes. Plus we can compress. I mean, we have tricks. We know how to do that. Yeah.
You said about bringing together developers and the team in general to help the system. What sort of organizational resources are available for that to take place? Is it a voluntary thing or is it for developers?
Yeah, people need to be paid, basically. Yeah, that's a problem, right?
Do you envision it being something where it's a collective effort, people to come together for the benefit of humanity, or is it an organization that has funding?
So this is still something I'm thinking about. You may have noticed that the Moore Foundation is part of my slides. Yeah. So because they basically asked me to start thinking about a new way to do science and someone was mentioning how we're gonna bring this side to the mainstream, but foundation like the Moore Foundation could be a good way to do that. So they may be interested in funding, giving some seed money to start this project. I don't know. I'm not talking on their behalf here, but we have good relationship. SETI Institute also have funding available for seed funding for specific projects. So we have to convince them about it. So yeah, there is venue. We cannot ask federal funding for this. I don't think this is gonna work. Sorry, one slide, please. Yeah. Yeah.
So I can see the supply and the demand. How, so things like, for example, this data is supposed to be open source, right? And so how, so I have a bunch of questions. Like, one is like, is any given marketplace built? That's my first question. And the second question is, given that it's all open source, how do you get customers to pay for that?
The second question I can answer to this. You're gonna have to tell me how to do that. Someone who have done that. I have some ideas, but I don't want to. There is people recording here, so I don't want you to use that later on. The first question is, what was it? Someone mentioned that there is one over there for data repository, but not for this type of data. For astronomy, maybe there is. Yeah, there is. Not yet. That's something I will do, but I wanted first to talk to you here to see if that's something doable, of course. This look like a bit of HiveMapper. HiveMapper. This is a difficult way for French people to say, I'm sorry. HiveMapper. Yeah? Yeah, thank you. You have a device, you have a token, people take data, bring the data. So I'm kind of interested in talking to them. In fact, if one day I can find someone to answer to me when I call, when I email. But that's the kind of same idea. Yeah.
How computer intensive is post-processing?
Super fast. I mean, super fast. We are working on different technology right now with the Laboratoire d'Astrophysique de Marseille and a company called Spaceable. So right now, in 1 hour, we can get in a frame, in a cube of data containing 2,000 frames. In 1 hour, we believe we can extract the information that will be needed. With on a very simple laptop computer, so it can be fast, it can be parallelized and get better.